Section 3.3 is titled Coplanar Force System. What we want to know how to do now is to apply Newton's first law so that we can establish that a particle in 2D space is in equilibrium. So consider an oil barrel. And it has some mass and it's being hoisted up. And to do that, they have two cables that's connected to a ring, and let's call that ring A, and it's attached to the oil barrel at points B and C. Another cable is being used at point A, and there's a hook, and we can foresee that it can be hoisted up by a force F. So what we want to do is perhaps maybe analyze particle A, the ring at A. So we'll assume that the particle of interest is ring A. So now what we need to do is look at the effects of each of these forces along each of these cables on ring A. So the coplanar forces that we are interested in are, let's say, forces in cables AB, AC, and let's call this point D, and then AD. To apply Newton's law to ring A, the first step is to draw a free body diagram. Draw a free body diagram. So the second step is to write the equations of equilibrium. The equations of equilibrium. And this, in essence, is Newton's first law. In order to apply Newton's first law to particle A requires that we find the resultant force in the x direction. We do this by taking the x component for each of these forces and adding them up. And it must equal to 0. We need to find the resultant force in the y direction, which is equivalent to finding the y components for each of the forces in these cables and adding them up, and must also equal to 0. These are called the equations of motion. Equations of motion. And they need to be satisfied in order for equilibrium to be established. First, let's do several problems to demonstrate how to draw free body diagrams. So examples on how to draw free body diagrams. So example 1. Suppose you have a ring and it's holding some kind of mass, and we'll call it mass M, and it's being held up by a cable using another fixture that's attached to a wall, and also there's another cable on another wall, and there's a fixture that the cable is attached to. And what we like to do is draw the free body diagram for this. We're also given that this is a 3, 4, 5 triangle, as well as the angle of this cable makes 30 degrees with the vertical. And let's label some points. Let's call this A, B, and C. The free body diagram for particle A would be shown as a dot. Then I would have a force due to cable AB, and it tugs at particle A. So I would have, let's call that force B. And we know that this would be a 3, 4, 5 triangle. We also have the effects of cable AC, and it would also tug at particle A. We'll call this force AC. It's located 30 degrees from the vertical. And we have the effects of the mass on this cable, and we'll call this just simply the weight. So that's the free body diagram of this system. Let's do example 2. Suppose you have a ring and it is held by a spring which is also fixed to a wall. In addition, this ring is being held by a cable that's fixed to a wall through this device here. And there's a force that's being applied at this ring with the magnitude of 600 newtons. Let's label some points. Let's call the ring A. Let's call the spring 1. We'll just call it spring 1. We'll call this C, B, and let's just call this force 1. So we want to be able to draw the free body diagram of the particle A that we're interested in. So we draw particle A. We draw the effects of the force of the spring, which pulls on A. So I would have that, and I would call it the force of the spring. We have the effects of this cable, and it would tug at ring A, and I'll call this force AB. And we have this applied 600 newtons at ring A. So this is a free body diagram of this system. Now, if they had given us some angles, let's say it was 30 degrees and this was also a 3, 4, 5 triangle, we would also indicate that on the free body diagram. We would say that's 30 degrees and that this is also a 3, 4, 5 triangle. Let's do a slightly more difficult problem. So we'll call this example 3. And suppose we have a particle A, and we'll call that just a ring, and there's a force that's being applied to it with a magnitude of 500 newtons. That ring A is connected to another ring via a cable at B. And that ring also has some force being applied to it with a magnitude of 200 newtons. That ring B is supported by a cable that's attached to a wall. Furthermore, ring A is also supported by a cable to a fixture that's attached to the wall. And let's call some of these points out. Let's call that A, B, C. Let's call this D. What we would like to do is draw the FBD of particle A. So I draw particle A, and I'm only interested in knowing the forces that are acting on A, meaning I'm not interested in this force because this force is acting on B. The effects of this force would definitely affect the force in cable AB, but for now, if I'm drawing the free body diagram of particle A, I am only interested in what affects it. So that would be the force in cable AB. So I'll call this force AB. The force in cable AD, force in cable AD, and also the 500 Newton force that's being pulled down. Suppose we were given some angles, and let's say it was 30 degrees here. Therefore, we know that it's also 30 degrees here. And we're also given this angle right here. So we need to transpose those angles onto the free body diagram as well. So that would mean I know this angle and I know this angle. And this is the free body diagram of particle A. So if we go back to the beginning of this lecture, our first step in analyzing a particle in 2D space is to draw the free body diagram. So the next step is to be able to write the equations of equilibrium. So let's do that. So let's say we're given the following system. We're given a particle, let's say, that's located somewhere in space, and there are forces acting on that particle A. In fact, there is a 600 Newton force pulling on it. There's also a force P of unknown value applying on it. And there's also a force F1 that's also pulling away at it, but in this direction. So let's establish a coordinate system. And let's say this is the X direction. And let's say this is the Y direction. And this problem also supplied us the following information, that this was a 3, 4, 5 triangle, and this was a 1, 1 triangle, which would make this radical 2. And they also let us know that this force F1 was at an angle of 60 degrees. They'd like for us to write the equations of equilibrium. Equations of equilibrium. So solution. And when you folks solve these problems, please make sure that you write it in this format: given, required, and solution. So that is actually the free body diagram of particle A. So that step has already been done. So first step would be draw a free body diagram. And that's sort of given. So the next step is to write our equations of equilibrium, right? So write equations of equilibrium. In order to do this, what I need to do is find the resultant force in the x direction by summing all the x component shown here in my free body diagram and make it equal to 0. Same thing for the y. I have to sum all the forces in the y and set it equal to 0. In order to do this, I need the xy components for each of these forces. So that's what I'm going to do first. To do that, I'm going to use a parallelogram method. and draw these parallelograms, right? Like that. And then the last one would be like that and like that. So I have these parallelograms, and I know that this would be my px. I'm sorry, this would be my py, and this force would be my px. I know that for this, that would be my f1x. And this component here would be my F1y. Similarly, we would do that for the 600 Newton force, where let's call this F2. So F2x, using similar triangles, so here's my similar triangle, would be 4/5 times 600 newtons. So 4/5 times 600 newtons. And it's headed in the negative x direction, so I have to put this negative sign. And my y component, my F2y, would be 3/5 times 600 newtons. And it's headed in the positive y direction, so I'll put a positive. Just to make sure that I know the direction, because these are very important. It's our responsibility to note the direction of these vectors. So now that I have the x and y components for F2, let's work on F1. So F1x, and F1 is unknown. So F1x would equal to F1 times cosine of 60 degrees. F1y would be F1 times sine of 60 degrees. Let's go to force P. Px would equal to negative a 1, 1 radical 2 triangle simply says it's at 45 degrees. So I'm just going to use that value, and therefore the x component would be p times cosine of 45, and the y component is also in the negative direction, so I would have a negative p cosine of 45 degrees. So what I have is all the xy components. The next step is to add each of those x components, set it equal to 0, and same for the y. So we get the following. I'm going to sum all the forces in the x, set it equal to 0, and I'm just letting you know that the positive x direction is to the right. Therefore, let's start off with p. So I would have negative p cosine of 45 degrees plus f1 of cosine of 60 degrees minus 4/5 times 600 Newton, all equal to 0. That is one of my equations of equilibrium. The sum of all the force in the y direction is equal to 0, and I'm letting you know that the positive y is going upwards. So I start off again. I get the y component. Let's do the same order. I get the y component. I would have negative p cosine of 45 degrees plus f1 sine of 60 degrees plus that y component, which would be 3/5 times 600 Newton equals 0. So this set of equation is the equations of equilibrium. for particle A.